Hi everyone, welcome back. With our next speaker, we are thrilled to present Elena Torró. She's a multimedia engineer born in Murcia, a great place to have delicious lemons and see beautiful arid landscapes. She loves experimenting with web technologies, playing with data, and creating stories through code. She also enjoys water sports, playing the ukulele, and writing science fiction stories, among other things. So, please welcome Elena Torró.
Hey everyone, thank you very much for coming to this talk. I'm really excited about it. I hope you all are safe and healthy and staying at home as much as possible. So yeah, this is the title of my talk, Algorithms and Data Structures on the Front-End Side. As they've said, let me introduce myself very briefly. I am Elena Torró. I'm a software developer, multimedia developer from Murcia, which is a region in Spain. You can find me at Twitter as Vice and Humans and in GitHub as Elena Torró, where you can see several contributions in open source projects, and I will upload there the slides of this talk as well. So the content of this talk may seem like some kind of computer science class, but what I wanted to do is to answer a question that I've seen many times, which is, should a front-end developer know how data structures and algorithms work? And I wanted to show some examples and some pieces of code, some problems that I've had to solve in my everyday job, and also some kind of just funny side projects that I've been working related with that. And so in order to see that, we are going to do a very quick review of what is an algorithm, about efficiency, complexity. Also, we are going to see different data structures. We are going to see what the big O notation is. And we will see that also through several examples as the ones that I'm mentioning here. All of them are written in JavaScript because even though lately I'm working more in Python, all of those are related with my everyday job. And we are going to see also a lot of things related with geographic information systems, because I've been working at a company called Carto for more than 2.5 years. And I've had to face there many problems that I had to solve on the client side using algorithms. So this is what I'm going to show in this presentation. But when this started, I remember that when I was 4 years old and I was learning the alphabet, I don't know if you had to do it in your school, but when I was a child, I had to memorize it to look for it in the dictionary. And I remember that I was learning it, and I thought, what if I want to search for a word that starts with S? I mean, I have to go from A through all the alphabet to get to this letter, which is near to the end. So I had an idea, which is to learn it the other way around. I asked my mother, and she thought I was a bit crazy. But what I didn't know back then, that what I was doing is actually to sacrifice a bit of memory in order to have more speed. So I learned it, and it has been really useful. Just like I'm going to say it very quickly in my mother tongue, which is Spanish. It is I know it sounds like very weird, but I don't know, it is a funny thing, and it's highly related with what I'm going to be talking today. So what is an algorithm? The very basic definition is a series of steps for solving a problem, and the efficiency is the study of the amount of resources that an algorithm uses. So In this case, for example, it may be the space of memory that I have to have in my brain to store an additional alphabet. And the types of efficiency of or things to take into account to measure algorithm efficiency is time efficiency. So how much time an algorithm takes to solve a problem. Also, space efficiency, as I said, if it's going to require extra memory. And also how complex the algorithm is. So what is complexity? Complexity is how fast or slow a particular algorithm performs for different input data. And this is the important thing, that to evaluate complexity, you need to know about your input data. So this is also very, very short. A data structure determines not only how data is organized or which is the type of your data, but also how you store it, how you retrieve it, how it's organized, etc. And I wanted to show here a real-life example where you can find discussions about structures and algorithms, even in Twitter. So here, for example, we are discussing an efficient way of saving unique names in an array. So here, there's a tweet where there is a bit inefficient way of doing it, and there are some suggestions here. So at the end, the writer of the initial tweet changes its mind and uses a more efficient data structure, in this case using a set that we are going to see it later. And well, I thought it was pretty funny. So what big O notation is? Well, in order to classify and measure the different algorithms and that we can use to solve the same problem, we use the big O notation. So this is a chart where we can compare the different big O notations from excellence to horrible. So I will try to go through this a bit quickly, because those are only examples of functions or methods that perform in this in the different times. So in this case, retrieving the first element of an array will always have the same cost, no matter the array size. And in this case, once we have a loop, we will see that this is the order of n. It scales in linear time. Then it starts to get a bit complicated. This one, O to the power of 2, we can see that we have here 2 loops, and in this case, the complexity starts to be higher. And yeah, I don't know if you've seen it, the famous Fibonacci recursive function, which is a very typical example when you start learning about recursive functions. And in this case, we have a function that grows in logarithmic time, because each time I is being doubled. And in this case, just a note, when you start to see a lot of nested loops, then just take into account that it is bad, and you have to avoid it as much as possible. However, it is important to take into account that, as I said before, the complexity depends on the input data. So maybe having this this previous example, is not that terrible if you know that the input data is not going to grow very much at all. So at the end, it's you have to balance between all the things that are involved in this measurement. So not only how the input is, but how is it used in each line, what would be the use case. And a very useful tool is to use benchmarks. So for example, this is just I have here 4 different ways of just assigning each value of an array to a variable. In some cases, you might just because of how your program or the code that you're writing is structured, you want to use one thing instead of the other. But for example, I had here I run this test, where as a result we have that the for I loop is the best option to solve this problem. Of course, this is a very, very small example just to illustrate how benchmark works. But at the end, of course, it will depend on many other factors. So don't rely only in a single benchmark, but have different benchmarks and ways to measure the performance of your algorithms. Okay, so now let's go also very quickly through different data structures. So we have here common array-like structures, which is the array, the stack, and the queue. I wanted to show here that in this case in JavaScript, what you are always operating with arrays, but the difference between those structures is the way you store and retrieve the data. And for this, there are no specific objects or classes in JavaScript, but so to use them, you will have to use external libraries or develop your own implementation. The same happened with linked lists, where the difference with an array is that you don't have to store the items in contiguous memory blocks, and each item is linked with the next one. However, depending on the use case, you may need to use an array instead of a linked list. For example, if you're going to do a lot of push operations. And double or double linked list is the same, but each item is also linked with the previous one, and you can access directly to the first and to the last element in the queue, or in the list. So an example of how to use a queue. In this case, we're going to see how to use the polygon poll inaccessibility to solve a very common use case, which is where to place the label of a geometry that represents a certain region. So not the centroid, which in this case will be like in the middle of the sea, for example, but somewhere where it's where you can see on a first sight that it means to label this geometry. So this algorithm was developed in 2016, and I linked in the bibliography all the links to the post, which is very, very interesting. And in this case, we are using a priority queue, which is basically a queue, but we are storing the elements having a priority value, where this priority is going to be the sum of the radius and these values of each cell. So the good thing of this solution is that instead of, in this case, in the previous solution was always looking recursively from bigger cells to smaller cells, and by adding this priority value to each cell, it increased a lot the speed of the solution, which is pretty cool. I've added here the code of this example. So basically, each cell will have a priority value. And this is the initial state. As I said, you will need to use external libraries. In this case, they are using one called TinyQ. And in the loop, we'll take into account basically the priority. That's all. So another famous data structure are hash maps, which are basically key value pairs. And one of the advantages of this is that you can retrieve any value by its key immediately. You don't have to look for this if you already know the key. So in JavaScript, it's very common to use, for example, JSON for this purpose. But it is not the only option that we have right now. We also have the map data structure, which also allows you to save functions and any other value as the key, which is pretty cool. You can know directly the size of the map by using the size property. And it works very good for frequent addition and removal of key pairs. So, for example, if you want to create or to have an ID generator for objects, you can use this any complex object that you have as a key, and then increment by one the ID that you are setting to this object. So you can know the ID of this object by only retrieving the object itself, which is pretty cool. And the other great data structure is the set. So we've seen in the Twitter discussion before, it allows you to store unique values, but it also saves these values in the order that they were inserted. And for example, we can use it to create a class that even though you set duplicated dates, by doing this, it will store only unique dates. However, there's a problem, which is that in maps and sets, those values are not garbage collected, and therefore the memory of your application can grow a lot. So to try to solve this problem, we have weak maps and weak sets. And I'm going to show you two useful cases. So for example, if, well, first of all, you have to take into account that they don't have the same methods than the non-weak respective data structures. So they are more limited. But for example, in this case, if you want to, for example, set that save a DOM element as a key and related to certain data, when, for example, you need to remove this element, eventually this value will be garbage collected from the set. And the same happens with the weak set that can be used, for example, to remove from the favorite items set those items that, for example, have been removed from a catalog. And an example of combining different data structures is, in this case, using an LRU cache, which is a cache that is going to save the items that were last recently used, as its name says, and it uses two data structures. So a hash map, which is great because the operation of insert and lookup, it's in average time the order of 1, it's in linear time. And there is a way of by using a double linked list of knowing which items have been created recently and delete the ones that not. So one practical use case that we did is, for example, in this visualization, we are visualizing items in different clusters, but each cluster has very particular information. And when you zoom in or you zoom out, then you have totally different data. And requesting this data every time you change the viewport is very expensive because you may have to retrieve a lot of data. So what we added is to only ask for the data of each cluster when clicking on it. So it will only do a request in this time. It will save it in the cache. So if you click later in the same cluster, you will have this instantly. But if you change the viewport very often, it's not going to affect the performance. So in this case, I think it's not very visible here, but there are different properties to identify a specific cluster. And this is a solution that we used. So I think I don't want to run out of time. I think I'm going great. We are going to see two last examples. One of them is, something that we are constantly using in the client side, which are trees. And the very basic example that we have is the document object model, which is the tree that represents the model of your HTML page, and it offers an API to manipulate this object. However, manipulating this object, I mean, pages have a lot of items, and when dealing with single page applications, those operations are really heavy. So in order to solve the problem of manipulating the DOM very often, people have created the virtual DOM, which is a solution. It's not a specification yet or something official, but is something that has been created to solve this problem. So very fast, I'm going to show you the what it does. Basically, it relies on two. So, which is that if an element that is being changed has a specific ID, then you can access it directly. And the other one is that if the element that you are changing is different, then you can replace it entirely. So in this case, imagine that you want to change this unsorted list, and you see that the element that you have changed in the virtual DOM, which is the copy of the original DOM, has changed, then you don't go element by element checking it. You will just replace it entirely. Okay, so the last example are graphs. Actually, trees are kind of graphs, but the difference is that in this case, there's no root element. And of course, I mean, there are many different graphs. There are directed graphs, cyclic graphs, but I wanted to show a practical example, which is, for instance, to represent polygons. Polygons that are adjacent to each other. And a very common situation is to visualize different regions in a map visualization. So in this case, we have a node for each country, and the connections between nodes represents those countries that are adjacent. So in a common problem is the ability to color, and this is the very last example, is to color each region. So there are no adjacent countries with the same color in the whole visualization. So there are many ways to do that. There is a theorem called the 4-color theorem that states that you need a maximum of 4 colors to color any visualization of polygons. So in this case, what we are doing is to have an adjacent matrix. So we will need 2 data structures, one the graph and another one the adjacent matrix. And in this case, it is initially sorted by valence, which is the amount of neighbors that a node has. So it will start using a color for the first one, and then it will try to use the same color for the second one, which is in this case the K. However, those are neighbors, so it cannot color in the same color, so it will go to the next one. And once it reaches the end of the adjacent matrix, then it will start using a different color. So if we keep doing this, then we will see how we have used, well, three colors to do it. Okay, so I did an example of this. In this case, I'm using also an external library called Graphology to create the graphs. And here what I've been doing is to initially set the colors to 0, so it's going to check, I mean, it is a way to check it has already been colored or not. And I'm going to show you a live demo of this using an open source library called Cartovial that we developed some months ago. And in this case, all the regions in this case are colored in the client side, because this is a vector library that allows you to color them directly using WebGL. And here is the algorithm that I shared before, and a couple of links with useful information. The colors are randomly generated, so I'm sorry if they're very ugly, but it was out of the purpose of this. Okay, so yeah, that's it. At the end, the conclusion is that there are many things to take into account, and it is good to know that those data structures exist, which algorithms and data structures you can use in the language that you're using to develop your application or to solve your problem. And at the end, there are many other factors that you have to take into account to solve a problem. So that's all. Thank you very much.
Thank you, Elena. Awesome talk. We have some questions. We need to go really fast.
Mm-hmm.
So the first question is not a question. Markdown for slides is amazing, and we're just gonna take one. What do you think about immutable data structures and libraries like Immutable.js?
I have never used Immutable.js, but again, I mean, I think that I've answered this in the previous slide. Like, it depends on the problem that you want to solve. So I don't know, and I will need to see like a problem where I would use this or not. And about the Markdown thing, I've also left here the links of the resources that I used for this talk.
Cool, awesome, thank you. So
thank you.
Digital applause, and stay tuned for our next speaker. See you soon.